years at this point. Primarily do networking classes, so like the Network Plus. I do the Cisco CCNA, CCNP Enterprise, CCNP Security, Linux Plus. So I like technical classes, so I focus more on the real technical side, as opposed to some of the ones that are just more theory based. I like to get my hands in on the technology itself.
Gotcha.
Yep. I've done tech edit work with Cisco Press for their books and all that. And that's about it, man. I really don't like talking about all that stuff. I like technology. So that's what we're going into. Again, man, you got any kind of questions whatsoever as we're going through, you just hit me up. Don't think twice about it.
Okay, will do.
All right, man. Here we go. So ports and protocols. All right, so any kind of networking class that you take, you're always going to get the idea of an OSI model being talked about, where they break things down into 7 different layers. OSI model was actually developed to understand the actual OSI protocol, but you have to go back years and years and years for you to sit there and really be making a reference to the OSI protocol. Today, of course, what's the most dominant protocol used in today's networks? It's TCP/IP. So where the OSI model is good when you first start learning, okay, I would sit there and say you really got to jump out of it and focus on TCP/IP instead, okay, because that's the model that's more practical. And one of the things that you notice right away is how the TCP/IP model is broken into 4 layers as opposed to the 7. And it kind of gathers functionality of the different layers of the OSI model into specific layers of the TCP/IP model. And what I'm trying to show with this graph here is that we have the application, presentation, and session all being mapped to the application layer of the TCP/IP model. Transport carried over transport. Network got renamed as internet. And then data link and physical gets grouped together to be referred to as network access. Some vendors, however, instead of referring to the TCP/IP model as network access on what would be that first layer, they sometimes refer to it as the link layer. The idea that you should be gathering here is those things that we define as application, presentation, and session are all being grouped up into application. And when it comes to what happens at the application layer of the TCP/IP model, we create the data. Then we pass that down to the transport layer, where we'll normally add TCP or UDP to it, okay? And at that point, then we're creating what's known as a segment, if it's TCP, or a datagram, if it's UDP. That segment or that datagram gets then passed down to the internet layer, where the most dominant protocol would be IP. Here we're adding our logical addressing. And then from there, we go down to the network access or link, where the most common protocol talked about there would be Ethernet, where we're trying to create our Ethernet frames just before we put them onto the wire so that we can transport it off to someone else. When it comes to application layer protocols, we got Telnet, SSH, okay, which are normally used for remote management purposes. FTP, SFTP, SCP, which are normally used for file transfer. Our email protocols are SMTP, POP, IMAP. Web browsing protocols, HTTP, HTTPS. One routing protocol that is claimed to be more application layer, as opposed to layer 3, like we see routing protocols down here, ends up being BGP. DNS for name resolution. SNMP, NTP, which are more management protocols. SNMP for Simple Network Management Protocol, NTP for the time protocol. Syslog, which is used for logging. Voice and video services. And then here's another routing protocol, RIP, which is kind of old, out of date, and not commonly implemented any longer. Now, what we're seeing with this graph is how we break these application layer protocols down. As they start moving down the protocol stack, they get encapsulated by lower layers of the TCP/IP model. So when it comes to Telnet and SSH, what will be added to it as we go down the stack during what's referred to as encapsulation is going to be TCP. Where if you were talking about SNMP or NTP, you're going down the stack. Then what gets added to it is going to be UDP. DNS here, the reason why the line is split is that sometimes it actually leverages TCP at the transport layer. Sometimes it leverages UDP at the transport layer. Our focus, of course, because this being ports and protocols, should be TCP UDP. Okay. Logical addressing, again, provided by IP. And then to get those frames across the network, okay, through our switching devices, that's where Ethernet or the network access / link layer comes in. When it comes to TCP, it is one of the core protocols that go along with TCP/IP itself. And one of the greatest characteristics of TCP is that it helps guarantee data delivery. Okay? If something was to drop, then TCP has a built-in mechanism to be able to retransmit that data. Where its alternative at the transport layer, UDP, doesn't have that mechanism built into it. When it comes to TCP, it is a connection-oriented protocol. And what makes it a connection-oriented protocol is the fact that it can go through what's known as the three-way handshake. Okay, so that this way, without doubt, it has the attention of the device in which it's trying to communicate with. Reliable data transfer. Okay, this is made possible because we use sequence numbers, acknowledgement numbers in a process that we refer to as a forward acknowledgement. Flow control, which makes it possible for us to control how much data is being sent by these segments at one given time. Windowing, okay, is something that can shrink and grow when it comes to TCP. In fact, when we talk about TCP, we actually claim that it's a very aggressive protocol, that it's always trying to grab more and more and more and more bandwidth until it can't, and then it drops down about a third of the way. And then it grows, and then it shrinks, and then it grows, and it shrinks, okay? This is a big difference when you compare it to, again, its alternative, UDP, that when we start a UDP-based conversation, we're putting information onto the wire, and then what ends up happening is it just consistent. If you started off with a 64K per second conversation, the next second is 64K, the next second is 64K, the next second is 64K, that's UDP. TCP, on the other hand, is trying to grab more and more and more and more and more bandwidth until it hits a threshold, and then it drops a third of the way. That's why sometimes when you're doing a download, that you end up seeing this like recalculation over and over and over again of how long it will take for that download to take place. You start downloading a file from the internet, it might start off by saying it's going to take 2 hours. And then a couple seconds later, it ends up being it's going to take 5 minutes. And then a couple seconds later, it ends up more settling around like, oh, it's going to take 30 minutes. What Microsoft's doing at that point is it's trying to take in consideration the window size, okay, as it's growing, shrinking, to kind of come up with an average to really see how long it would take for that information to be finally downloaded. When it comes to TCP, we also have error detection. Now, the error detection and the reliability of data transfer, not really the same thing. When it comes to reliable data transfer, we're using those sequence numbers, those acknowledgement numbers to guarantee that data delivery. I send you something, you send me acknowledgement. I send you some more, you send me acknowledgement. Okay, that's the reliable data transfer. For error detection, what we're really doing is we're making sure that the data, or the segment itself, is not corrupt. If it was, then we know not to further process it, not waste the CPU's time. Let's just discard that segment, okay? Now, when it comes to TCP, the discarding there, not a big deal, okay? Because we have a good idea that it's going to be retransmitted due to the reliable data transfer concept. The error detection is just really making sure that what's about to be processed, okay, is not corrupted. When it comes to TCP, there's also congestion control. This is going to be possible with a technology known as ECN, the explicit congestion notification. What ends up being the case is that there can be a device in the path, typically a router, that might be seeing that it's overwhelmed, that there's so much data that it's receiving, but there's very little bandwidth for it to continue to forward. Well, when that output queue uh, starts to fill, just as we're putting that information onto the wire, if it got the full capacity, then what has to happen is that that router has to start dropping that traffic. There's no more room in the queue. Therefore, we can't sit there and slip those segments onto the wire itself. So what can the router do? The router can then send an explicit congestion notification to that client that says, hey, slow down. I'm being overwhelmed by all the information that you're sending. Okay. Let me free up my queue some, make some space. Okay. So I'm not dropping your traffic. So with explicit congestion notification, a form of congestion control, what can happen is an intermediary device like a router can sit there and then say to a client, okay, slow down. Don't keep sending me so much information. Okay, let me catch up. Let me free up this congestion problem so that this way I'm not prematurely dropping your traffic. When it comes to TCP, we have many different protocols that work at the application layer that can leverage it. Some of the more common are going to be that HTTP, HTTPS again for website browsing, our email protocols such as SMTP for sending an email, FTP for file transfer, and also remote administration where you might be telnetting or SSHing to a device. They both end up using TCP as their transport protocol. The three-way handshake. Again, when it comes to TCP, we get the attention of the device in which we're trying to communicate with. And to get that connection made, we go through what's known as the three-way handshake. It's during the three-way handshake that will establish the initial sequence numbers and acknowledgement numbers before passing the data between the devices. Again, it's those sequence numbers, acknowledgement numbers that help guarantee the data delivery. We need to know what numbers to begin with, okay? During the three-way handshake, we establish that. So when it comes to the three-way handshake, not only are we trying to set up these initial sequence numbers, acknowledgement numbers, and also window size to help guarantee data delivery, but we're also getting the attention of the device that we're trying to communicate with. Looking at this picture here, I'm going with this PC being our client, this box here being our server. We begin a conversation with the only TCP flag being turned on is known as a SYN. The server, once it receives that SYN, responds back with both a SYN and an ACK flag turned on in the segment. To complete the three-way handshake, the client responds again, but this time only with the ACK flag turned on. From this point on, they'll continue their conversation in which both the SYN and the ACK flags are lit up, turned on, and they're passing actual data between each other. However, when it comes to the TCP three-way handshake, there is a bit of a vulnerability to it. There is a concept that a bad actor could take advantage of known as the TCP SYN flood, in which they're trying to perform, which would fall into the major category, a denial of service attack. The SYN flood is when we only see 2/3 of the three-way handshake take place. In this case, I'm going with a bad actor here, is sending that segment where the only flag in the TCP header that's turned on is the SYN. The server, the victim in this case, is responding back with what's known as a segment that has the flags turned on of a SYN ACK. But what never occurs is that final acknowledgement. The three-way handshake never completes. And unfortunately, what happens is that this server ends up then getting overwhelmed, possibly, with a bunch of partially opened connections. Sooner or later, this server is not going to be able to fulfill a legitimate request from a legitimate host, and that's why we call it a denial of service. Now, normally the way that this is implemented by bad actors, I'm switching over to OneNote here. Normally the way that this is done by a bad actor is that they sit kind of a couple step, they sit a good step back from what appears to be the attack. That the bad actor ends up being this CNC device, sometimes referred to as a C2 device. Okay, I've heard it referred to as command and control or command and conquer. And this is your true bad actor. What they normally do is they take advantage of these other systems, which are sometimes referred to as bots, zombies, drones. And what are these bots, zombies, and drones? They're collections of computers that are most likely not patched. And therefore, somebody was able to figure out how to take remote control over them. And what this CNC device will do is that it'll talk to these bots, zombies, and drones and pass messages to them, trying to get them to be synchronized so that this way they can perform that SYN flood in the direction of, say, maybe a web server. Now, all of a sudden, thousands of bots, thousands of zombies, thousands of drones end up overwhelming this web server with a bunch of half open or partially open three-way handshakes in which we never actually finish that last leg, that last acknowledgement. Here, the web server has a bunch of partially open connections and therefore later on not able to fulfill requests of legitimate hosts. This is where the major category would definitely be DOS, denial of service. This is more specifically referred to as distributed denial of service. And then even more specific than that, this would be called a SYN flood. And that's again just taking advantage of how TCP works with its three-way handshake. To help mitigate that SYN flood, we got a bunch of different security concepts that could be slipped in. One of them is configure a firewall. Firewalls can help mitigate SYN floods by looking at the TCP header, looking at the flag field of the TCP header, and identify when multiple SYNs are coming in that never complete to form that full three-way handshake. With ACLs and again some firewall rules, we can use the established keyword. The established keyword makes it possible to where connections coming into your organization, if they don't have the ACK flag turned on, they're just not allowed. And then there's also TCP intercept. So looking at these three. So here you have a router, maybe a firewall. Here's your internet. And then you have a device that you're trying to protect. Again, we'll call it a web server. Now, the TCP intercept concept is that on this router, on this firewall, as the name kind of implies, it puts itself into the middle of the conversation. It intercepts the TCP three-way handshake to where a user out on the internet starts by initiating a conversation to that web server with that SYN. Instead of going all the way to the web server, the router, the firewall, intercepts that three-way handshake and responds back with a SYN ACK. And if that's it, the firewall can be configured to drop that connection much faster than what the web server can be configured to do. Okay, it can identify itself as being attacked, okay, or what would have been the web server being attacked, and then go ahead and then reset, okay, that connection, bring up those resources faster than the web server might have the ability. If, however, we actually see that final acknowledgement come back in, and that three-way handshake does actually take place completely, then what happens is that this device configured with TCP intercept it'll then go ahead and replay that three-way handshake to the web server. There's that SYN, the same one you're seeing here. Here's that SYN ACK, the same one that you're seeing here. Here's that final acknowledgement, the same one that you're seeing here. And then what happens is that this router, this firewall, kind of gets out of the way and allows this client and this web server to continue to communicate with each other, okay? At most, monitoring the connection, but no longer focused on that TCP three-way handshake concept. Pretty popular technology to kind of alleviate any kind of stress that the web server might have. Let's put that burden on that firewall, on that router, so that it does the verification of the three-way handshake before the victim could possibly be compromised or possibly put in that denial of service scenario. On a Linux server, so this would be more on that server, that web server, okay, as opposed to the intermediary device that I just went through with this TCP intercept. We can go ahead and control a setting known as TCP max SYN backlog. This makes it possible to identify how many open TCP connections the server is willing to support. Most servers are configured for 4096, but if a device was under a TCP SYN flood, as an immediate response, administrators might have to sit there and change that number to be something higher to accept more connections, at least temporarily. Again, when it comes to TCP, our conversations that are built will be from host to host, not host almost to the other host, okay? We could have a whole world of internet between PC-A and PC-B. It won't make a difference to a TCP conversation. It does go from A all the way to B. After we go through that three-way handshake, once A and B have each other's attention, then they can start transferring data between each other. And we know that our data is getting to its destination because the receiver will respond with an acknowledgement. Here I could see PCA sending a segment with a sequence number of 15. And then B responds back with an acknowledgement of 16. When it comes to TCP, it uses what's referred to as a forward acknowledgement. So instead of saying, I got what I got, rather what it does is it says, I'm ready for the next. So when I send you a 15, I know that you received it because you basically respond back with, I'm ready for 16. So now what do? I send the 16, and since I was successful the first time, I'll go ahead and add maybe another more data. So here's another sequence of 17. Now when B receives it, it doesn't acknowledge each. It only acknowledges the last one in sequence. So if I successfully receive the 16 and the 17, then how do I respond back? I'm ready for 18. Here I can see 18, 19, and 20 being sent. When B receives it, it then responds back with acknowledgement 19, which is not good. It should have responded with a value of 21, but it didn't. So now what has to happen is as the sender, PCA, I have to retransmit. By saying I'm ready for 19, I know that they received this segment, but they didn't receive this one or this one. Now what do I have to do? Retransmit this 19. So here's the retransmission. What you also notice is that the window size of this conversation that was growing, one segment, two segments, three segments. Once we see that drop take place, what does then TCP do? It drops its window size because we want to make sure our network stays as efficient as possible. We don't want to put ourselves in a situation to where we're constantly transmitting information that's being dropped and then retransmitting it. That's a waste of bandwidth, okay? So what we do instead is that when you send me an acknowledgement, if you didn't receive all the segments that I previously sent, then the window size shrinks because we don't want to consistently overwhelm the devices that are in the network, that are in the path, okay, that may have limited how many segments made it all the way to PCB, nor do we want to overwhelm PCB because it might be having a bunch of different conversations and it's being swamped from other sources. Let's not make it to where PCA is adding to that overwhelmingness. So we shrink that window size. That should then keep the bandwidth in check. So we're not just wasting it by constantly retransmitting, retransmitting, retransmitting. This idea of when I send a 15 and I get back an acknowledgement of 16, that's the forward acknowledgement. And you can see here how TCP leverages those sequence numbers and those acknowledgement numbers to help guarantee data delivery, a concept that goes with TCP, but not UDP. When it comes to TCP, in its header, there is a flag field. And when you start a conversation, what's the only flag that's turned on? It's the SYN. After you start the conversation, okay, you will normally see the SYN flag turned on every packet from that point on, okay? There is a little bit of an exception on part of that three-way handshake. But the other flag that gets constantly turned on is the ACK flag. So once we initiate a conversation, we normally see both the SYN and the ACKs turned on inside the TCP flag field. When you're done having a conversation, we want to free up those resources. So that's where the FIN flag comes in. When the two devices are done communicating, they'll send each other's fins, say that the conversation's done. It's a graceful close to the conversation. Now both devices can free up resources that can be used in other conversations. A reset is an abrupt end to a conversation. This normally happens because of a security appliance. You might have an intrusion prevention system or sometimes an intrusion detection system that identifies that there's an attack that's taking place within your enterprise. With IPSs and IDSs, what they can do is they can send reset messages to the victim. They can send reset messages to the bad actor to try to get them off of each other, try to reset that connection itself so that this way those resources aren't being used up by my victim and I can kind of terminate that conversation prematurely, okay, by sending those reset messages to the attacker. UDP is the user datagram protocol. So where TCP, we say that it creates segments. UDP, we say that it creates datagrams. When it comes to UDP, it really is your alternative to TCP. Both TCP and UDP, they are transport layer protocols. Where TCP is connection oriented, UDP is connectionless. There is no three-way handshake when it comes to UDP. There is no, let me get the full attention of the device that I'm trying to transfer the data to. There's also no guarantee of data delivery. There is no sequence numbers. There is no acknowledgement numbers. Okay, that's a TCP thing, not a UDP thing. So when data is being sent, how is it sent? I send more, I send more, I send more. I'm never waiting for the acknowledgement. When it comes to UDP, we have less overhead. The less overhead is really being provided by two concepts, really. One is we don't have the three-way handshake, so there is no lingering connection between the two devices. Also, the size of the UDP header is smaller than that of the TCP header, so therefore less bandwidth used to the overhead of the protocol. Therefore, we should be able to send more data if need be. Why do we even have UDP compared to TCP? For services that end up being time sensitive. When speed is critical and are real-time services like voice and video, they can't be held up. They can't be waiting for these acknowledgments. They need to send, They need to get their data to the destination in a timely fashion. We're talking voice over IP phone calls. They're UDP based, not TCP based. We're talking streaming video services like RDP, remote desktop protocol, to where you're connecting to a device's remote GUI, working from it as if you were actually sitting at the computer itself, normally UDP based. When it comes to streaming video services, this might be conference calls, that's UDP. That might be surveillance cameras, that's UDP. Any kind of real-time services, streaming voice, streaming video. Which of the two, TCP, UDP, do we use? It's UDP because we don't want that overhead. We don't want to hold up those conversations. Other protocols will leverage UDP as well. We have UDP is used by NTP, the Network Time Protocol, SNMP, the Simple Network Management Protocol, and then remember DNS, that actually leverages both TCP and UDP. But when you're sitting at a computer and you type in www.yahoo.com.google.com, how do you go ahead and resolve that name to an IP address? That's a DNS query that is being sent. Okay, that is a UDP-based conversation, not a TCP-based conversation. Now, if you told me that two DNS servers were trying to update their databases, well, that's not UDP, that's TCP. And it kind of makes sense why DNS is uses TCP and UDP. It makes sense that it's TCP based when two DNS servers are trying to update one another to make sure that their names, the IP address associations are the same. They're working the same database. Because if that process was to fail, if that synchronization was to fail, then who could be impacted? Thousands of users. Everyone pointed to that DNS server could be impacted if that synchronization doesn't go well. However, if I'm sitting at a computer and I type in www.google.com and that UDP DNS query was to fail, who's affected? It's just me. And most of the time, what do I end up doing? I just refresh the browser and it works just fine the next time round. Okay. So the idea of DNS query messages being UDP based does make sense. Where we're looking for that fast resolution, if it fails as a conversation, one user impacted. But if you're talking about two DNS servers updating their databases, better known as a DNS zone transfer, we want that to be TCP based because if that synchronization of databases was to fail, who could be affected? Thousands of users. So we want that guarantee. We want that zone transfer to be TCP, not UDP. Comparing here my TCP and UDP headers. So the first thing that I notice when I compare the two headers to where I really know both of them are related to the transport layer of the TCP IP model is the idea of ports. Source port, destination port, source port, destination port. Ports provides a concept known as multiplexing, which I'm going to be getting to, I believe, the next page. Other characteristics that make the TCP header stand out as when compared to the UDP is going to be the sequence number, acknowledgement number, and window size, which I've always kept it straight as SAW. Sequence number, acknowledgement number, window size. We know the sequence numbers and the acknowledgement numbers, they work together to help guarantee data delivery. We know the window size is used to control the number of segments that are being sent at a time. The TCP flag field, that's where we saw the SYNs, the ACKs, the resets, the FINs. The checksum is used to make sure that the segment has integrity. If we fail our checksum check, okay, then what ends up being true is we know that the segment was corrupt. Let's go ahead, discard it, and then TCP, with that natural mechanism to guarantee data delivery, will then just retransmit that information. The urgent, like you would think, it's indicating that the segment is urgent and therefore should be processed immediately. And then there's some options that you can use with TCP to enhance its functionality, give it more functionality when it comes to communication across your network. Okay, some enhanced features is the idea, the option field, which actually should be my next page. The UDP header, right away, it's smaller, therefore less overhead on my network. It does have a checksum though, but the checksum isn't used to guarantee the data delivery. The checksum is just being used to make sure that what we're about to process isn't corrupt. The checksum should be optional, so it won't always be found in the UDP header, but I don't see a great reason not to take advantage of it if I was to write some sort of application, because let's get rid of that unwanted, that corrupted information so I don't hang up some sort of process, okay, when processing that data in the future. TCP header is normally anywhere from 20 to 60 bytes in size, while the UDP header is typically 8 bytes in size. Those TCP options, those enhanced capabilities that can be offered to TCP include maximum segment size. Maximum segment size is how we can control how big the segment is that we're about to transmit. The reason why I make adjustments to this, one of the technologies very common set up between two routers or two firewalls when passing traffic from site to site through the internet ends up being GRE tunneling, possibly IPsec tunneling. And these tunneling protocols, what they do is they add additional overhead to our packets. So what was already 1,500 bytes in size, what does GRE, generic router encapsulation, what does IPsec do? It adds on top of this. So what was 1,500 bytes in size gets even larger and larger and larger. Well, this 1,500 bytes, known as the IP MTU size, can become problematic for networking appliances. For example, when a switch sees something that's too big, above that 1,500 byte IP MTU, it just says to the frame, "You're too big. I can't process you," and then drops that traffic. Routers, on the other hand, when they see something that's too big, what did they do? They compensate for it. What they do is what is referred to as fragmentation. They take that big packet and they ended up breaking it up into smaller pieces. The problem with fragmentation is, as a receiver, I have to get all those fragmented pieces before I can reassemble things and then pass it up the protocol stack itself. So when it comes to IPMTU size, it's 1,500 bytes. When things are too big, switches will drop that traffic, routers will fragment that traffic. To help keep that from happening, I can adjust this IPMTU size to compensate for those additional headers that will be added by IPsec and GRE. And when you do that, you normally want to adjust the TCP MSS size. So by modifying the maximum segment size, that'll help then keep the IP MTU size in check so that we're not going above that 1,500 bytes, causing problems of switches dropping and routers fragmenting traffic. Windows scaling. Windows scaling is in reference to a concept sometimes called long fat networks. In today's data centers, how fast are we moving the data between our appliances? Well, when I first started, we're talking 100 megabits per second. Then it was gig. Then it was 10 gig. Talking today, 40 gig, 100 gig between your devices is not a surprise at all. One of the problems, though, that we face when we try to provide these huge bandwidth connections between appliances is that when we monitor them, they often don't get that full utilization. They don't go to the 100 gigabit per second bandwidth utilization. We end up seeing that these large pipes end up not being fully utilized. And why does that happen? Because the conversations going across these connections, they can't scale up high enough. They can't create segments that are big enough to actually utilize all the bandwidth of these long, fat networks. So one of the things you can do in the option field for TCP is enable what's known as window scaling. So that this way you can increase the size of those segments so that you can really leverage the idea of the 100 gigabit connection between our appliances. I believe you should always be looking into window scaling. Whenever you see speeds between devices go above the 10 gigabit per second. When you get greater than 10 gigabit per second, and you only have so many conversations going across that connection, look into window scaling, because when it comes to window scaling, it's going to get me the ability to use possibly the other 90 gigabits per second. Selective acknowledgement, sometimes known as SAC. This is going to give us the ability to add an additional acknowledgement field when it comes to TCP-based conversations. What could possibly happen is I send a segment that has a sequence of 1, maybe another that's 2, another that's 3. And remember, the acknowledgement going back should be, I'm ready for 4. So then I transmit the 4, the 5, the 6, and a 7. My window size grows. When I get the next acknowledgement, it ends up saying 6. So what ends up being the case? Successfully received the 4, successfully received the 5, but now what do I have to retransmit? The 6 and the 7. Well, with SAC, by adding an additional acknowledgement field, what we possibly give this conversation the ability to do is, what if 6 wasn't received, but 7 was? If this was received, acknowledgement 6 says retransmit the 6 and the 7. But with an additional acknowledgement field, okay, due to SAC, selective acknowledgement, the 7 could be said as being received, I'm ready for 8. So now the source device knows I don't have to retransmit the 7. All I need to do is retransmit the 6 and then continue on with the conversation, going with the 8, 9, 10, 11, and so on. So when it comes to selective acknowledgement, all it does is add one additional acknowledgement field so that this way, when I receive some of the segments, but not all of them, they end up not all being contiguous. That additional acknowledgement field means that I can send just the missing segment and not all the duplicated information. Again, keeping my network as efficient as possible. Not having to retransmit this 7 keeps the network very efficient. Timestamping can be used. There's some technologies that like to add additional timestamps so that we can really get great time measurements of how long it takes for data to get through our enterprise. When it comes to TCP and UDP, what's one of its biggest concepts? It's ports. And why are ports important? They provide the idea of multiplexing. Why is that necessary? Well, having a device support more than one service at a time is quite common. So let's say that I have a server. Its IP address is 1.1.1.1. Well, any client trying to send data to this server, what IP address does it target? 1111. But let's say that this server is a web server as well as an email server. Well, if I was trying to communicate with this server, the web server service, versus the email server service, sending the 1111 really isn't good enough. But if I send the 1111 port 80, then the server knows that it's trying to target the web server application. And if I sent the 1111 port 25, then we know that we're trying to target the email server application itself. What do ports provide? It's the concept of multiplexing. It's the idea of being able to differentiate different services that are running on the device by not just targeting the device's IP address, but also its port number, making it possible for us to then differentiate the traffic that's going to the web server service versus the email server service when both services are being hosted by the same device, the same server, the one that's configured to use the IP address of 1111. Ports provide multiplexing. And of course, both protocols, TCP and UDP, leverage ports. When it comes to starting a conversation, source port will be randomly generated, and then destination port ends up being well known. So when we start a conversation, the client that initiates, they'll randomize their source port, but that destination port is going to be associated to a service that falls in the range of well-known port numbers. When it comes to an IP address, every IP address has a port range of 0 to 65535. And it's the first 1024, so 0 to 1023, they're considered the well-known ports. And we call them that, and you can kind of think back in any other networking class that you may have taken. We call them well-known ports because you got port 80. That's HTTP. That's in that first 0 to 1023. 443, which is HTTPS. That's in that 0 to 1023. 22, which is SSH. 23, which is Telnet. 20 and 21 for FTP, so forth and so on. Any class that you've been in that's networking related in the past, what ended up being the case, they gave you a bunch of port numbers to memorize. And where were the majority of them found? In that range of 0 to 1023, the well-known ports, which are mapped then to applications, well-known applications. If looking at the picture that's in front of you here, you can think of the device that's in front of you as a client system in which I'm running a telnet application, like a terminal program like PuTTY or Secure CRT, an FTP application like Mozilla, an HTTP application, which of course you would know better to be a web browser. On this client system, as I'm using these apps and they're generating traffic, they end up going down the protocol stack. And sooner or later, they'll hit the OSI model layer 4, the transport layer, or the TCP/IP model transport layer. And then that's when source ports and destination ports get added to the conversation. The source port, again, ends up being this random value. The destination port is going to be that well-known. We continue down the protocol stack where we get that logical addressing at layer 3. We get that physical MAC addressing at layer 2. Get ourselves all the way out to this router over the wire. And when the router responds back, what does it do with the source and the destination ports? It flip-flops them. What was the source is now the destination. What was the destination is then the source. Why is this useful? Well, here we have this client running these multiple applications. We're sending the data to the router, we're sending it to the web server. When the web server responds back, let's say both conversations are returning at the same time. How do I know the data that should be going to my terminal program, my telnet application? The destination port. The source port that I use to start the conversation should be the destination port that's coming back. That's how I know this conversation goes here and this conversation goes here. Those ports, again, what are they doing? They're providing multiplexing for us. Again, every IP address has a port range of 0 to 65535. It's that 0 to 1023 that are referred to as well-known ports. Registered ports are the range of 1024 to 49151, and then dynamic private ports are that 49152 to 65535. The well-known ports are the ports that we normally have to memorize. The registered ports sometimes get associated to different applications. Like when we talked about, when I mentioned previously RDP, the remote desktop protocol, I know it uses 3389, and that's in that range. If you're into authentication services like Radius, I know that they typically use the two ports 1812 and 1813 for the purposes of authentication, authorization, and accounting. So that port range, those registered ports, they're sometimes registered to different applications, different services, but they're not in that well-known range. The private ports, okay, are often used for the purposes of those randomized ports that you saw in that previous page. When I start a conversation, the source port is randomly generated. Source ports will typically use any port it wants in the range of 1024 to 65535. However, what really controls the range that will be used as that randomized source port is your operating system. Windows 49152 to 65535 maps perfectly back to the dynamic port range that I showed you on the previous page. Linux systems, though, they go from 32768 out to 60. Oh, that's way too many numbers there. That two is not supposed to be there. 60999. Again, these client-side ports, they're randomly generated to be used as a source port to a conversation. This would be some well-known ports. When we initiate a conversation, these would be my well-known. When the return traffic's coming back, okay, these ports would be used as sources. So when I start, this would be a destination port, but for that return traffic, it would be a source port. Most classes, I would say these are very, very common port numbers that get talked about. And if you end up taking like a Network Plus or Security Plus or even a CCNA, they might ask you to memorize these ports to get yourself prepared for the exam. Then I start going into some routers and firewalls here. But I've gone an hour, guys, and I over prepared. I had a bunch of information to go through. Yeah, we've already gone an hour, and that's what this is supposed to be. Anybody have any questions at all?
No, this has been a great presentation. So it's made me think about some of the stuff that I'm involved with right now with AI.
Oh, cool. Very good. Yep. I don't have an easy way of getting it out to you. I don't have everybody's email address. Did you give that information to training camp already?
I did.
Okay. So what I'll do is I'll make sure that this presentation, I'll throw it into a PDF, and then I can ask training camp to send them out to you. I don't know if that'll help you out in the future.
That would be awesome.
Yep. I know they were also planning on recording the conversation itself, so I think they're going to put it out on the website and everything if you want to go back and take another look at it.
Cool.
Yep. And then, yeah, I want to say that that's about it, guys. Portia, Sarah, I know you guys jumped in just a few minutes late. You barely missed anything at all. I was just getting started. Did you have any questions at all?
No, thank you so much. I do look forward to the recording.
Okay, good. What was bringing you into the webinar today?
Knowledge, looking to expand.
Okay. All right, good stuff. Well, all right. Well, I won't keep you guys. I'm sure I'm sure some of you are on lunch break, so I won't keep you guys. Let you guys go back to work. Yep. But staying in touch with training camp. I know they're doing these webinars on a regular basis. So if you want to jump back in on another one, feel free to do so. Maybe I'll even ask them if I can continue on with the presentation later on in the future itself, because I really didn't even come close. I got 43 slides. I made it up to 16. So there's a lot more that I wanted to get into because I wanted to start talking about securing it with firewalls and SE Linux, the idea of NAT and all that kind of stuff. I kind of ran out of time on that. All right. All right. Well, thank you very much for being here. I appreciate it. My name is Brian DeAndrea. If you got any questions, pass them through training camp. I'm sure they'll get them out to me.
Thanks again.
All right. You have a good one.
You too.
All right. So long.